YouTube? Beautiful Mind here. I was really liking that music. I kind of want to let it ride. I like the vibe. So let's see. Okay, so this is going to serve as a lecture for, this is coming from I think it's like week 4, day 8 for calculus for business. We're almost done with chapter 2. So we're going to be ready for exam 1. It should become available next Wednesday and be available from next Wednesday, which is a week from today. I guess it's the 24th until that Sunday. Okay. Let's do all of our assignments are due weekly, Sunday night at midnight going into Monday. You can actually submit any assignment late, but it'll be a 10% late penalty, and we get a limited attempts at all assignments, okay? You access it, it's basically Pearson, but I linked it to Blackboard, so you access it through Blackboard. Okay. So with section 2.5, we're going to be looking at exponential decay, more applications of exponentials and logs, and more specifically, we're going to be looking at exponential decay. Some objectives here. We want to find a function that satisfies dp by dt equals negative kp. We want to convert between decay rate and half-life and solve apply problems involving exponential decay. So we have this equation, dp by dt equals negative kp, where k is positive, shows that p to be decreasing as a function of time. So the rate of change of some function p as time changes, in this case, is going to be a negative decay rate, right? And so the solution p of t equals p naught e to the negative kt shows it to be decreasing exponentially. So this is exponential decay. The amount presently initial at time t equals 0 is p naught, right? So I think before we had the exponential growth model where, this was like a equals per pe to the rt. But now our rate is going to be negative, so we're going to explore exponential decay. Now, if we differentiate this, we'll get this guy here, right? The derivative of exponential is itself times the derivative of the exponent. So the derivative here is just going to be negative k. So we're going to have negative k times this thing, but this thing is p. So that's where this guy comes from, right? Okay. It took me a while to realize that. Like I did the derivative and it wasn't matching up. I was like, why isn't this matching? I was like, oh, P is this guy, right? It took a little bit for that to dawn on me for some reason. Anyway, so exponential growth where K is positive, this is the general form of an exponential, looks like this. We have a horizontal asymptote. It generally passes through 0, 1 here, and we have exponential growth. Exponential decay when K is, basically we have negative kt, right? Because if k is positive times a negative, then basically we have exponential decay, and it generally looks like this. We still have a horizontal asymptote being the x-axis or the t-axis here, and it still passes through the point 0, 1, right? But instead of exponential growth, we have exponential decay, okay? So the decay rate and the half-life are related. Let me show where the half-life comes from. So let me introduce a page. Okay. So like if we wanted to explore half-life, so let's start with like exponential decay function, right? So we have p equals p naught e to the negative kt, right? And so if we want the half-life, we want to find how long it takes for half of that material to remain. So if we start with p naught, we're going to finish with half of p naught, all right? E to the negative kt. We can divide both sides by p naught and we get 1/2 e to the negative kt. We can take the natural log on both sides to get the t, because we're going to solve for t. So if we take the natural log on both sides, on the left, natural log of 1/2 is the same as natural log of 1 minus the natural log of 2. Ultimately, that becomes negative natural log of 2. Okay, and on the right, we're going to have negative kt. Divide both sides by negative k, and the half-life, which is our t, is going to be the natural log of 2 over k, right? I feel like that context makes this a lot easier to digest, right? So let me see, they're using KT and natural log of 2, right? So the first one, K times T equals natural log of 2. You can see it here. If we multiply both sides by K, we'll get our KT equals the natural log of 2, right? Half-life. And then you can just basically through algebra, switch these around as needed, right? The way I'm used to seeing it is this guy here. So I'll probably kind of be doing it that way. So the half-life is going to be the natural log of 2 over K. Okay, but I just wanted you to see this backstory on where that came from. Okay, so in this example, hang on a second. Let me close this out because that's distracting. What did I close? All right, I'm gonna try to let it be. Hopefully the music's not too loud. The audio that I hear I have the music for you all slightly higher than what I hear, and it's very, very faint for me. So hopefully it's not too loud for you. Okay, in this example, plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.0028% per year. What is its half-life? Okay, so we can just use the half-life formula. We don't have to start from the exponential decay model. We just said that the half-life equals the natural log of 2 over K, right? So I'm going to write it like this. The half-life equals the natural log of 2 over K. So if they want half-life, they gave us K, so then that's going to be the natural log of 2 over, so if that's a percent, so here, it has to be in the form of a decimal, 0.0028. Now this percent symbol, you can look at that as per 100. You can look at percent as per 100. So you can replace the symbol with 1 over 100, right? So if we do that, we're going to have the natural log of 2 over 0.0028, basically divided by 100. All right, so move the decimal to the left twice. So then 0.000028 under the natural log of 2. Then I'll use the calculator there. Okay, I think I have a typed version of this. I just wanted to get to that point. We have 4 zeros and 28. You see the 4 zeros and the 28? Use your calculator, you should get this number. Okay. Well, there is a little bit of a delay, but okay. I'm gonna let that be. So quick check, I usually leave these as exercises. Depending on my time and how I feel, I'll come back and do these if needed, but everything is there, so it'll be good practice. Maybe if you're practicing on your own, try to take the original question and try not to look at the answer, and then work it yourself, and then compare what you get with what they get. And if you can consistently match up, then that's a good omen, right? You're on the right track. Example 2, the radioactive element carbon-14 has a half-life of 5730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping for one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? Let me see. Radioactive element has a half-life, so they give us a half-life, okay? So if they give us half-life, natural log of 2 over K. Okay, what are we trying? How old? We're trying to find the original time. So let's introduce the exponential decay model as well. P naught e to the negative kt. Okay, we're going to kind of flow between those. A radioactive element has a half-life of 5730. Okay, so we have H. The presence of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping for one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. So let's see, we can solve for K. We want to solve for T. It lost 20, so whatever it started with, it was down by 22.3%. Okay, so let's start by solving for K. Let me give myself another page, some space here. Okay, so the half-life was 5730, right? So if the half-life, and let's do like this will be a little bit better too. 5730. Okay. So then that means that 5730 equals the natural log of 2 over k. So we can solve for k. K is going to be the natural log of 2 over 5730. Okay, I'm going to use my calculator. I'm not going to show the calculator. I think you can crunch this number. It's nothing fancy going on here. But I do have to load it. Okay. So if I did the natural log of 2 divided by 5730, let me see. I'm tempted to leave it. We get this long decimal. I'm going to leave that as k like that just to kind of keep it exact. Okay. So we have our k. We're trying to solve for t. It says that 22 found that the linen wrapping for one of the scrolls lost 22.3% of its carbon-14. How old was the linen wrapping? Okay. So we're trying to solve for t. So it started with some unknown amount, right? We have our exponential decay formula. P equals P naught e to the negative kt. So we started with some unknown amount. We're going to leave it as P naught. But we finished with 22% down. So we would say 100 minus the 22%. So we're 23. Let me see. I'm just going to use my calculator. So I'm going to say 100 minus 22.3, 77.7%. So I'm going to change that percent to a decimal. So that means that what remains is 0.777 of the original, right? I just kind of wrote it like that because I'm out of space. I'm just going to move this stuff over, right? So what remains was basically 77.7% of the original. So then we get this e to the negative. I'm going to leave k exact. I'm going to not round until the end. You don't have to do it this way. I just like to do this to keep it exact. When you're using decimals, especially when you round early, try to just take the long decimal. Take the decimal out as far as you can, because you really don't want to round until the very end. So that's why I leave it exact. The only thing we don't know is t, right? We can solve for everything else. Now we can divide both sides by p naught. So these are going to cancel each other out. We can take the natural log of both sides, okay? So if we take the natural log on both sides, on the left, we're going to have the natural log 0.777. On the right, we're going to have negative this number, 5730, times t, right? Ultimately, t is going to be the left divided by that number in front, that coefficient. So t is going to be equal to the natural log 0.777 over, we can say negative natural log of 2 over 5330, nope, 5730. That's it. That's the exact answer. And then I'm just going to crunch it put it in the calculator to get an approximation. So I'm going to do the natural log 0.777, close parentheses, divided by, I'm going to put a negative in the very front. So I'm going to insert a negative and then divide it by parentheses natural log of 2 divided by 5730. Okay. So I'll close off the denominator. The time, I get about 2085.8 years. So I'm going to say that I get approximately 2085. I'm going to say 0.8 years. Yep. I think it's accurate. Okay. Let's go like this, and let's copy, and let's compare it to what we have already typed, right? So first it says find the decay rate K, right? So you see this, natural log of 2 divided by 5730. I left it here. They took this decimal, right? I didn't want to round early, okay? Then substitute the information from the problem into the equation. So the amount, the future amount equals the initial amount. Basically, P equals P naught E to the negative KT. So this is the same formula that we use. So then the amount remaining right here, we got that number. It was it lost 22.3% of its carbon 14, so that means 77.7% remain from the original. And then this, that long decimal, right? Long story short, approximately 2086 years. I think that's exactly what we got. 2086, you see it there. Okay. So the linen from the Dead Sea Scrolls, and they did theirs a little bit differently. They kept the long decimal. I left mine as a fraction to keep it exact until the end. Okay, but we got the same result. That was fun. Let me see my time. We're looking pretty good on time. Okay, let's keep it moving. I can get rid of this. How old is the skeleton? Oh, this is a quick check. I'm going to leave that as an exercise for you. Okay. Again, my recommendation, take the original. Just try to get the original question without looking at the answer. Work it yourself. Take it as far as you can, and then compare it to what they did. Because that's essentially what I'm doing with these other examples, essentially. Following the birth of their granddaughter, two grandparents who want to make an initial investment of P naught that will grow to $10,000 by the child's 20th birthday, want to make an initial, okay. Interest is compounded continuously at 4%. What should the initial investment be? Okay, we're going to use this, and I'm going to give myself some space. I'm going to add a page. They want the final amount to be 10,000, and is compounded continuously at 4%. Okay. So they want their future amount to be $10,000, right? $10,000. There, we want to solve for P naught. That's what we want to. In this case, let me call it A naught. So the starting amount, they want to solve for that. Let me see what units did they use. Okay, let's try to use the units they're using instead of switching it up. This is the future amount. This is the initial amount. The rate, or K, was I think it was 4%, and the time was 20 years because it's about her 20th birthday. Okay, so we're going to be using P equals P naught E to the KT. We're using the exponential growth model, not exponential decay, because we want this to grow over that time, right? So let's plug in, and so we want to solve for P naught, the initial deposit. So we want to finish with $10,000, right? P naught, that's what we're trying to solve for. EK is, 4% as a decimal is 0.04 times 20 years, right? So all that's just a number, so that means the initial deposit or initial amount is going to be this E to the power of 0.04 times 20 under 10,000. Okay, I'm just going to use my calculator to crunch that number. Okay. So then I'm going to say 10,000 divided by E to the power of 0.04 times 20. Okay, close off the denominator. So I get 4493.29. So I get approximately 44. Dang, that's interesting. So if you want them to have $10,000 on their 20th birthday, and you have an account that pays, but see, I can't find accounts that pay that kind of interest. I've been looking. Only thing that's honestly behaved like that I've found access to, that I have access to right now, are like stocks. They're more risky and a lot more volatile, but that's the only thing that comes even close that I have access to, that you actually have access to as well, that pump out those kind of interest rates. It's all very interesting. 29, right? So they need to deposit $4,493.29 and just leave it that account and let it sit for 20 years, and then if they set that up, if that starts at her birthday, when she becomes 20, she'll have $10,000. Hell, I'm almost 40. I don't have anything like that where somebody's been letting it sit to have that. I've definitely spent that kind of money, but yeah, okay. But it's just interesting. It's like thinking long term. You got to think 10, 20, 30, 40, 50 years at a time, right? Okay, let's compare this to what the text gets. 44.93.29. Okay, we got the same thing. They need to deposit 44.93.29, which will grow to 10,000 by the child's 20th birthday. That's so much fun. You know, there are some other ones that are really interesting. If you like, if I had access to a stable account that paid 4% and I had a steady flow of income, I already know what I would do. Like like if you have an account that has that kind of interest, like if you had an account that had 5% interest and you made a deposit of $1 million, I know that sounds like a lot, but it's doable. With that setup, the lowest form of interest is simple interest. That's like $50,000 a year. So with an account with $1 million deposit and it has an interest rate of 5% per year, that's a full time check. That's like a couple of $1,000 a month, just for that account sitting there. Like that's what I've been working towards for the longest, and want to like set stuff up that behave in that manner, as many as I can, and share them with as many, like free as many people as possible. But hey, it only works if you only touch the interest. Don't ever touch the principal. If you touch the principal, it'll stop working. And so as long as that account is open and everything is clicking, a couple of $1,000 a month. All right. I think that's you can live off of that if you play your cards right. Like, I think that's fantastic. I just get excited at the thought of it. I'll get there one day though. Maybe one of my students will hit it big or connect me, and Mr. Pfeiffer, I appreciate what you did. Bam! I'm putting it out there in the universe. You never know what's going to happen. You have to be open to the different ways that these things can manifest in your life. That's a quick check, so I'm going to leave that as an exercise for you. We have a little over 10 minutes, okay? Yeah, we need to kind of keep going. So theorem 11, the present value P naught of any amount P due T years later at an interest rate of K compounded continuous. Basically, present value of an amount due T years later. Oh, they kind of reversed it. Because P naught is the starting amount. That's interesting. I don't know why they would do it this way. It's like they kind of just they did the compound interest in the exponential decay formula, where P naught is usually the starting amount and P is the future amount. But because it's exponential decay, that's so strange to me. Newton's law of cooling. The temperature T of a cooling object drops at a rate that is proportional to the difference T minus C, where C is going to be a constant temperature of the surrounding medium. Thus, the rate of change of the temperature with respect to time is going to be negative K times T minus C. The function that satisfies the above equation is this guy that you see here. The temperature based on time, A times e to the negative kt plus a constant. So a body is found slumped over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. She waits an hour, takes the temperature again and finds it to be 93.4. She also notes that the temperature of the room is 70 degrees. When was the murder committed? I like this one. Okay, so what I'm going to do, I'm going to just take this formula at the bottom, T of T, AE to the KT. Okay, let me give myself a page. I think it's, here it is. Okay, let me add a page. Okay, so let me do paper like this. All right. So the temperature based on time, I think it said it was AE to the negative KT plus a constant. Let me go back and check that formula really quickly. AE to the negative KT plus C. All right, okay, let's fill in what we got. She arrives at noon. So at noon is when she arrives. I'm just writing out what we have. The temperature is 94.6 degrees. 94.6 degrees. Do we have the units there? I guess it would be Fahrenheit because Celsius is like almost boiling. Yeah, so it shouldn't be boiling. That should be Fahrenheit. I'm just gonna write Fahrenheit. Okay. She waits 1 hour, so then at 1 p.m. the temperature is 93.4, right? 93.4 degrees Fahrenheit. Okay. She also notes that the temperature of the room is 70 degrees. So the room temperature is 70 degrees. Okay. Then it says when did the murder happen? When was murder? Okay. Let me see if I can use this before looking for any help. We have 2 points, right? So let's let noon be 0. Let's let noon be time equals 0, right? So at the start, or when the time is 0, the temperature was 94.6. So we got this 94.6 equals e to the negative k times 0 plus some constant, right? So e to the 0 is 1. So then ultimately we get 94.6 equals a plus c. Okay. So that was when I'm letting noon be 0. Let me make that note. When was the murder? We're going to say let noon equal 0, right? Okay, so we get this one. So let's plug in the second one, the second piece of information. So an hour later, the temperature is 93.4 degrees, e to the negative k. The t in this case is now been 1 hour. So our units here are hours. Plus some constant. Okay. So then what does that become? Are we introducing another variable? We are. Let me think about it. Is that constant? Is that the room temperature? Let me see, where C is the constant temperature of the surrounding medium. Okay, so we have C. Okay. So then the room temperature is 70, so that's our C. So let's go ahead and plug that in. So this is 70. Right here we have 70. And then here we also have 70. So I think from the first one now, we can solve for A. So that means that A is going to be, what is that? 24.6? 24.6 degrees, okay? Or 24.6, right? That's A. I guess give myself another page. Let me add a page. View, seamless, okay. So we solve for A. Now we can take this A and plug it into the second equation. So then we get this 93.4 equals this 24.6 times e to the negative k plus 70. Okay. Notice here we have everything except k. So if we solve for k, on the left, if we subtract 70, we get 23.4, 24.6 e to the negative k. Okay. So we're going to keep solving for k. We can divide both sides by 24.6. We'll get e to the negative k equals 23.4 over 24.6. Take the natural log on both sides. So negative k equals the natural log of 23.4 over 24.6. And multiply both sides by a negative. I'm just going to move the negative. So it's going to go right here. Okay. So this is an equation or an expression for our rate, right? So we know K. So let's see, we're trying to solve for T. Let me see. So again, the general formula, we got K, we have C, and we have A. Let's put all this together. So then A is 24.6. Let me see. We just solved for K. And C is 70. Okay. So then again, we're using the temperature based on time is going to be A times e to the negative kt plus a constant. So our formula, the temperature based on time is going to be this 24.6 times e to the negative K. So it's going to be natural log of 23.4 over 24.6. Again, you could take that decimal times t plus 70, right? So let me think about it. We want to solve for t, but we need to know what's the temperature, the initial body temperature. We know the temperature when we got there. There's one place, let me see. There's, other than like, I'm thinking like maybe the standard temperature of the human body, 96.4. But you don't know that that was the temperature of the body. But I mean, I think that's the piece of information, missing piece of information that we need. Let me see. We're gonna let T be the time elapsed in hours. It represents noon. Coroner took. We did all that. We got that. We got this. Right. We're gonna let that be. Number of hours since the murder. We must find K. We did that. We got our K. Right. We got. I think we got the same K. Okay. We're gonna let that be. Right. And then you need the temperature to determine the time of death, assuming the individual had a normal body temperature of 98.6. So this is all based on what their initial temperature was, right? So like if we're wrong about this initial temperature, then that would throw things off. But you see, that's the part that we needed, was the 98.6, right? I think we're okay. I'm not going to keep working because we're pretty much there. You plug in, you assume that the original temperature was 98.6, and then solve for T, subtract the 70, divide by 24.6, natural log, and divide by 0.5, right? You see it here. So we assumed that the original body temperature was 98.6, and I think we got everything else is the same. You can first subtract, I would subtract 70, you get the 28.6, divide by 24.6, okay? You see it there. Take the natural log on both sides, you get this. Divide by negative 0.05, and we get approximately 3 hours. So the murder more than likely happened around 9 a.m. Okay. Let's go to view, single page. Okay, that was fun. Yeah, like something like that. I mean, yeah, to know that, okay, the general temperature of the human is 98.6 degrees Fahrenheit. Okay, I think that kind of wrapped this up, and we're right on time. Okay, so we explored the decay rate and half-life. We talked about where that came from. We explored some using present value and exponential decay, and then we applied it to a concept of Newton's law of cooling. Okay, and so as you kind of make your way through this material, just write down your questions. You either have to email me. If I don't respond to your email in time, you have to ask me. Just ask me during class. Like, that's a simple thing, because that's the whole point. Like to use class time to kind of answer these questions, to kind of make it easier for everybody. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.